Hello students, Stride here again, ready for section 6.3, periodic trends. Your objectives for this section, you'll need to be able to compare period and group trends of several properties, relate period and group trends to atomic radii and electron configuration. Some new vocab. Old review vocab, principal energy level, the major or outermost energy level of an atom. Main idea, trends among elements in the periodic table include their size and their ability to lose or attract electrons. So, a lot of new stuff in this one. Section 6.2, a lot of review. Here we're getting a lot of new stuff. Atomic radius. The atomic size, periodic trend, influenced by the electron configurations. You have metals. The atomic radius is defined to be half the distance between adjacent nuclei in a crystal of the element. If it occurs with a molecule, the atomic radius is half the distance between nuclei of identical atoms. So we measure in a metal such as sodium half the distance between the centers of the two atoms, and in something like hydrogen, a diatomic molecule, half the distance between the two atoms that are bonded together. General decrease in atomic radius from left to right, the first of our periodic trend. And as you'll have to understand these trends, and I want you to understand why they occur. And this is caused by a increasing positive charge in the nucleus. So as we move left to right across the periodic table, we're gaining more protons in the nucleus. And this generates a larger electrostatic force, causing the atoms to get a little bit smaller. You got a larger attraction, more protons, more electrons, more force pulls it closer together. And here's a mini version of a periodic table showing as we move left to right across the periodic table, the atomic size gets smaller. Lithium's a little bigger than beryllium, a little bigger than boron, carbon, nitrogen. Again, there are going to be some exceptions to this trend. In all these there'll be exceptions, but this, we're talking trend. Here's one where it gets a little bigger. The atomic radius generally increases as you move down a group. So, going down increases. And as we said, it decreases as we go across left to right. These are trends in the atomic radii. And the reason it increases as we go down is because we're getting to higher energy levels, meaning we have much bigger orbital size. And we got a thing called ionic radius. Here, an ion, an atom, or a bonded group of atoms with a positive and negative charge. Ions are formed by gaining or losing electrons. When they lose electrons, they'll form positively charged ions, and they'll always become smaller. Loss of a valence electron can leave an empty outer orbital, smallest radius, and we get more electrostatic repulsion, allowing the electrons to be pulled closer to the radius. When atoms gain electrons, they are always going to become larger, causing an addition of electron increases electrostatic repulsion. So the metals tend to lose electrons, and their ions are much smaller than the atoms, and nonmetals tend to gain electrons, and the nonmetal ions are much bigger than corresponding nonmetal atoms. So here we have little different looking trends, but as we go down, ions tend to get bigger. As we go across over here on the left side of the periodic table, our ion size decreases while we're in the metals, but then when we get over into the nonmetals, the negative ion size decreases too. But it does not decrease all the way across. We have to break it into two groups. So, ionic radii of positive ions generally decreases from left to right, and the negative ions also decrease from left to right. So here it's broken into a blue category and a yellow category. And here we can see that. We got all these nonmetals, or these metals over here, and in this metal area, as we move left to right, the size decreases a little. Then we get bigger again when we get over into the nonmetals. But then, as we move left to right within this area, they get smaller. Another trend we're going to look at, ionization energy. Here we've got the definition. Ionization energy, energy required to remove an electron from a gaseous atom. And energy to remove the first one is called the first ionization energy. And we can have a second ionization energy, a third ionization energy, and so forth. Good. And here this chart shows you the period ionization energy of elements in periods 1 through 5. In period 1, as we move left to right, ionization energy goes up. As we move across the table in period 2, ionization energy generally goes up. You can see little jumps in there where it's not going up. And the same thing with period 3 going up, period 4 going up, period 5 going up. And you can have some little discrepancies in there, but the general trend is as we're moving left to right, ionization energy is increasing. And we get definition for that second ionization energy I mentioned earlier. And each successive ionization requires more energy, but not a steady increase. So, here's a chart showing ionization energies for the period 2 elements. And note, if you look at each of them, you're going to see at some point it's going to jump up to a very large value. Going to have a great big increase. So each one, as you move down here, you start getting a really big increase. And this would have to do with the valence electrons. As we get, the valence electrons are much easier to strip off than non-valence electrons. So when we jump into that next energy level, after all the valence electrons have been removed, the level goes up. It's down here on the bottom one. Neon has 8 valence electrons. Their ionization energies for that first 8. reasonably small in comparison to trying to do this ninth one, which goes into the next energy level. So, jumps up a lot. The ionization energy, the large increase related to number of valence electrons. Mentioned earlier, first ionization energy increases from left to right across the periodic table. First ionization energy decreases down a group because atomic size is increasing, which is moving the electron farther away from the nucleus, meaning it's going to be easier to pull it away. So here's our chart illustrating the ionization energies in the general trend. So this is for first ionization energies. So generally increases as we move left to right, generally decreases as we move down. And we got a thing we call the octet rule. Octet rule states that atoms tend to gain, lose, or share electrons in order to a full set of 8 valence electrons. As we've been drawing electron dot structures, you'd get to like a noble gas such as neon. It has 8 electrons around it, 8 valence electrons. That is what we call a stable octet. And other elements will, as they react, will always typically try to get to that stable octet, the octet rule. So, octet rule is going to be very useful for predicting what types of ions an element is likely to form. And we get electronegativity. Another definition. Electronegativity of an element indicates its relative ability to attract electrons in a chemical bond. So somewhat the opposite of ionization energy. Ionization energy is talking about removing electrons. This one's talking about attracting electrons. And electronegativity decreases down a group and increases left to right. So, increasing electronegativity, decreasing electronegativity. Most electronegativity element up here at fluorine, and then down here we'll find, for the most part, our smallest electronegativity. If you remember, fluorine is the most electronegativity, and it gets smaller moving away from it. We'll be using this electronegativity numbers for some work we'll do later. So, a couple quick review questions. Make sure you understand the answers here. Well, with science and energy, ionization energy first, because the second ionization energy is going to be more, third more, fourth more. So, lowest first. Ionic radius of a negative ion becomes larger when? So if you're moving up in a group, ionic radius is going to become smaller. If you move left to right across a period, ionic radius, or right to left, ionic radius is going to become smaller. Move down, it's going to become bigger. And losing electrons is going to make the ionic radius smaller. And negative electrons gain anyway. Yeah, that's all we got for section 6.3. As always, we'll be doing a lot more problems in class, a little more discussion on it. Well, brief summary on section 6.3. So that's all for now.